So far, we've been talking about objects which were either rotating or translating through space. Today, we'll consider an object which is doing both. Namely, its center of mass is moving to the right with VCM, and it is also rotating about its own center of mass with angular speed, omega. And we're going to consider three cases. Case one, we're going to consider VCM, which is less than r omega. Case two, VCM, which is equal to r omega. And case three, VCM, which is greater than r omega. In each of those cases, let's consider what happens with the point which is in contact with our surface. Assuming an ideal sphere, there should only be one such point. Now, that point has some motion due to the motion of the center of mass, VCM, but it also has tangential speed, V tangential, which is equal to r omega. And so now let's consider what this means in each of our cases. In case one, the velocity of the center of mass, notwithstanding our diagram, is less than r omega, which means that the point in contact with the surface slips backwards. When v is equal to r omega, in fact, these both cancel out, and we are left with a point which is stationary relative to the surface. And finally, when v is greater than r omega, we slip forward. And those are our three cases. For your intuition, if this feels unintuitive, we can think of case one as something like a car which is stuck in snow. Its translational velocity, or its motion forward, is slower than the speed with which its wheels are spinning on the snow. Conversely, something like 3 could be an object which is slipping on ice. It is moving forward faster than its wheels are spinning. So let's first consider an object in case 3. And let's take the extreme. We'll take an object which is moving with speed v equals v naught and omega equals 0, such that clearly v is greater than r omega. And so what happens to this object? So let's look at a free body diagram of the object. We obviously have our force of gravity, mg, acting at the center of mass, and Fn acting at the point of contact, upwards. And if there's no friction, what we can see is that first, there is no net force, so v will not change, and also that there is no net torque about the center of mass, and so omega won't change either. But now let's assume that we have friction. What we've noticed is that the point in contact with the surface slips forward, therefore our force of friction would act to the left. Moreover, because we are actively slipping, we know that the force of friction is kinetic friction, so that we can say the force of friction is equal to mu Fn, and of course, in this case, on flat ground, our normal force is mg. So now let's consider what will happen to our velocity and our omega as functions of time. So our goal is to find v of t and omega of t. To do this, I want to find both my linear acceleration and my angular acceleration, and we can do those independently. So we know, of course, that our velocity will be equal to v naught plus at. And let us find our acceleration. Our acceleration will be to the left opposite of v naught, so it will be negative. Our net force will be negative mu mg, and this will equal ma. So we can write that v of t is equal to v naught minus mu, our masses cancel, so minus mu gt. That is our velocity as a function of time. And now let's consider our omega as a function of time. We'll notice that Fn and mg exert no torque. And so our only torque is due to the force of friction. We can say that mu mg r, notice we are at a 90-degree angle, so sine 90 just gives us 1, is equal to I alpha. And let's consider this as a disk, so we'll say I is 1/2 mr squared alpha. Great. And so therefore alpha will be equal to mu 2 mu g over r. And this then allows us to say that our omega of t, we're starting with 0 angular velocity, so omega of t will be 2 mu g over r times t. And there we have it. So let us now consider what happens over time. We can clearly see that V is increasing and V is decreasing and omega is increasing. We started off with V greater than R omega, but we're slowly going to be transitioning to V equals R omega. And in fact, we can solve for this by saying, let's find the time when V naught minus mu GT is equal to R times 2 mu G over R T. And I will leave this equation as an exercise for you to solve. What will happen once we've reached that time? Well, at that point, we're now back. We are now in case 2, where the point in contact with our surface is stationary. And what that means is we transition to the realm of static friction, which recall is adaptive. In this case, remember, static friction is adaptive. There is no force on our object to the right. And so our force of static friction will be 0. And we will stop accelerating and maintain our rolling without slipping condition.